All right, guys, today we have an important one called sampling distributions and estimators of a statistic. Remember, a statistic comes from a sample, some kind of number that comes from a sample. Sampling distributions, important concept for what we're going to be doing the next few weeks. All right, here's what a sampling distribution is. A sampling distribution of a statistics such as a sample mean or sample proportion. Now, those two are just statistics that come from a sample. A mean is, the average of some kind of measure from a sample. A proportion is almost like a probability of something happening in a statistic, such as like a proportion of boys and girls being born. Proportion of boys being born in a sample would be like 0.5, and the proportion boys to total or girls to total, like a probability, is a distribution of all values of the statistics when all possible samples of the same size are taken from the same population. So basically an infinite number of samples are taken. That's the sampling distribution. The sampling distribution of a statistic is typically represented by a probability distribution in the format of a table, a histogram, or formula. And hope that made some sense to you. Basically, we're going to take tons and tons of samples, or we're going to look at tons and tons of samples, and this is called a sampling distribution of a statistic. All right, the sampling distribution of the sample mean, talking about means now, sample mean is known as X bar, is a distribution of all possible sample means with all samples having the same size. So yeah, let's go back to the boy-girl thing, births. So let's say I take sample sizes of 100 and find the average, or find out how many baby boys are born, for example. So I take one sample, there were 55. Take another one, there were right at 50. Another one, there were 49. Another one, there were 49. Another one, there were 52. Then there was another one that was 50. Another one was 53. Then there was one that was just like 40. And one was just like 62. One that was 58. One that was 41. One that was, and these should all be X bars. These are all means from the sample. Also, I guess the portions, but anyway, that's what's happening. So just looking at the distribution of all sample sizes, of all sample means based on all these samples having the same size. So in my case, they were all sample sizes of 100, and those are all the means. So look at the next slide. Look what happens when you do that a whole lot. Well, what happens is, two things I want you to notice real quick. First of all, underline right here in red, all our sampling procedures need to be random. Don't forget that. From way back in chapter 1, when we first started the year, all our samples we collect need to be random. The population mean is known as mu. So what I do is I take sample 1, see how many. Sample 2, look what the mean is. Sample 3, look what the mean is. So I know the population mean sometimes is mu. Here's what my sampling distribution did. There's all my sample means that I took, all the X bars, those are sample means, and look what kind of distribution it gave me. Yep, you guessed it, a normal distribution. And that's going to happen always when you do sample means, when you take a sampling distribution of a sample mean. If you take all the possible samples of a statistic, your mean is going to be a normal curve, which is kind of cool because that means we can do a lot of stuff with it. All right, sample means. Target the value of the population mean. They have basically, that's what says this. Let's just read the parentheses. That is, the mean of the sample means, that's all the sample means, is the population mean. The expected value of the sample mean is equal to the population mean. The distribution of the sample means tends to be a normal distribution, which is what you just saw on the last slide. So if you find all the sample means and take that mean, it's the same as the population mean. So that's how we find population means. We take sample after sample after sample after sample, average those means together, and that gives us a great estimator of what the population mean is. The sampling distribution of the variance. Variance for a sample is known as S squared because remember it is the standard deviation squared. Is a distribution of sample variances with all samples having the same size, taken from the same population. So the same definition basically, except we're doing variances instead of means. And I'm just going to make this a little quicker, I'm going to show you what happens with all the variances from the same population if you take all the samples. And here we go again. First of all, make sure your sampling procedure is random. Select n values and find this variance. The population variance is little sigma squared. Take sample 1, there's your variance. Sample 2, there's your variance. Sample 3, the mean of the population we know is little sigma squared. Now the difference with the variance is is that when you look at all the samples put together, you get a right skewed distribution. Is not normal, which you're probably expecting because the last one was normal. But variances aren't. They are always right skewed, and that's important to know. And if they're always the same, that means we can use them to estimate the population's variance, which means we can really get standard deviation that way. So let's summarize here about the variances. Sample variances target the value of the population variance, which means if you take all those all those samples and find the variance in them, if the samples are the same size from the same population, then you're going to get one that is skewed. But here we go, right skewed. That is, the mean of the sample variances is the population variance. So if you find all those variances, find the average of them, that's the population variance. The expected value of the sample variance is equal to the population variance, which means the same thing. And the distribution of sample variance tends to be skewed to the right. It will be skewed to the right. One more here. The sampling distribution of the proportion, which is known as p hat. That's known as p hat because it comes from the sample. P hat is a distribution of sample proportions with all samples having the same size, taken from the same population, the same kind of definition, but now we're doing proportions. And really and truly, when I think back to that problem we had at the beginning with the boys, girls, I was really doing proportions there instead of the average. So the proportion is, how many boys total over how many kids total. So that's the proportion, or kind of a probability. Right, this is what I just told you. The population proportion is known as P. We did P, remember doing the N times P times Q, where P was the proportion or probability of success. That's the same P. P hat comes from a sample instead of a population. So P hat, sample, just P, population. Proportion, not just total number of population. All right, one more of these, same old looking slides. Randomly is underlined again. Make sure when you do a sample, make sure it's a random sample, a simple random sample usually. Don't forget the proportion of the population is P. So you take a sample, you get a P hat. Sample 2, P hat. Sample 3, P hat. And again, P hat is some kind of proportion. The boy-girl example, however many boys you get out of 100, that's your proportion. How many girls you get would be a proportion. The mean of the population is P. There's our distribution. And look what kind of distribution it gives me. A normal one. All right, so no surprise there. The only weird one was the variance. It was right skewed. The mean sample distribution, and also the proportion. Sample proportions give you normal, which means we can do a lot of stuff with them because think about how much stuff we've done with normal distributions already. All right, here we go. Summarize. A sample proportions target the value of the population proportion, which means they give you a great estimator. That is, the mean of the sample proportions is the population proportion, and that's the expected value of the sample proportion is equal to the population proportion. That's what you expect. Again, if you average all the sample proportions, that's going to give us what the population proportion is, and because they're normal, it's a normal distribution, the mean is going to be in the middle of our normal curve. The distribution of sample proportions tends to be normal. Just saw that on the last slide. All right, sample means, variances and proportions are called unbiased estimators because once you have those, once you find the average of the means and variances proportion, they target the population parameter. They give you the parameter for the population. These statistics are better in estimating the population parameter. So these three, the mean, the variance, and the proportion, unbiased estimators. They tell you pretty much what the population parameter is. Sample medians, ranges, and standard deviations are biased estimators, which means they do not target the population parameter. They do not tell you what the population parameter is. However, one big note here at the bottom, because we use standard deviation all the time. The bias with the standard deviation is pretty small, especially in large samples. So a lot of times we do use S, which is sample standard deviation, to estimate baby sigma, which is population standard deviation. So even though it is a biased estimator, the bias is small in standard deviation. So if the population is big enough, we do use it to estimate. All right, let's take an example here. It says, consider repeating this process. Roll the die 5 times. Find the mean, the variance, and the proportion of odd numbers of the results. So First question, what do we know about the behavior of all sample means that are generated as this process continues indefinitely, which means it doesn't stop? Here's what we know about rolling a die. Those numbers right there, 1, 2, 3, 4, 5, 6, are all equally likely to occur. So to find the mean, you just add the divided by 6. This is what we would, that's the mean of the whole deal, of the population. If we did it forever and ever and ever, find the average, keep finding the average, it's going to get closer and closer to 3.5. That's our population mu. All right, so let's look at what happened here on the next slide. What I have here is a sample of 10,000 trials. They rolled a die 10,000 times and found the average. Sample one, they rolled it 5 times. The average number they got was 3.4. Rolled it 5 times, 4.4. Rolled it again, 2.9. Now, one thing you need to notice is all those are different because they're samples. Every sample mean is going to be different. But once you start averaging those means together, you're getting the mean of the mean. Look what happens. In 10,000 rolls, the mean became 3.49. Remember what we just said on the last slide. We know the population mean is 3.5 because, if you just average up 1, 2, 3, 4, 5, 6, divide by 6, you're going to get 3.5. So look how close it was in 10,000. Now, if you continue to indefinitely, if you kept on going, the mean will be 3.5. And look at the distribution of all the samples. Those are all the samples. And look how close to normal that is, which is what we just found out a minute ago. Sample means, we do a sample distribution of sample means, it's going to be normal, very close to normal. So we're going to use a normal distribution when we talk about and do calculations on that. Okay, same deal. Found the proportions. How many times do we expect an odd number? Well, obviously, if half the numbers are odd, we would expect to get odd half the time. All right, so 50% or 0.5. So what we did is we did 10,000 trials. We wrote it 5 times, got 0.2. Another 5 times, got 0.4. Another 5 times, 0.8. So notice none of those are 0.5. We're not getting an odd number half the time very often. But when you average the average, when you take all those and average them together, we know the mean of the population should be half or 0.5. You should get an odd number half the time. Look what our distribution looks like for 10,000 trials. All right, pretty close to normal, which is what we talked about earlier. And because we're equally likely, the population of odd numbers is 0.5. The proportion of 10,000 was also 0.5. If continued indefinitely, if go forever, it will be 0.5. Also notice it is normal. Now, 10,000 doesn't guarantee we're going to get 0.5, but we're going to be darn close to 0.5 if we don't get 0.5. And the more you do, the closer you're going to get, and eventually we're just going to get 0.5. So proportions, probability of something happening, it's going to approach the population the more you do it indefinitely. So good stuff there. It's going to be normal. Okay, every time we sample, this is just extra kind of, but every time we sample, we take one of our samples from the population, we're going to sample with replacement. Sampling without replacement would have the very practical advantage of avoiding wasteful duplication, because sometimes you may get the same sample twice. However, we're going to do replacement for 2 reasons. One, if you do a small sample, it doesn't make a significant difference whether you replace it or don't replace it. And, number 2, sampling with replacement results in independent events that are unaffected by previous outcomes and are much easier to do calculations with. So lots of advantages for doing it with replacement. The only disadvantage really is that you could get the same exact sample 2 times. But if you can do an infinite number of samples, that's really not going to matter. One word of caution, and this video is over. Finally, many methods of stats require a simple random sample. Don't forget that. That's way back in the day when we first started statistics. That's the reason we talked about these. If you use such a voluntary response or convenience, even though you do all your other stats on them, you're going to get very bad results because your sampling method was not good. You need to have a very good sampling method before you start any of this stuff to make sure that your samples actually have some kind of accuracy to them, so good results. So sampling method is so important, even though we haven't talked about it in a while. It's extremely important. So that's why I underline all the random samples today. All right, hope it made some sense. May need to watch some of it again. It's a very important video. We'll work on it in class tomorrow like we always do. See you then.